This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Welcome back, very warm welcome back to our first afternoon session. It's going to be a great session with ideas of variational circuits, embeddings, expressivity questions and transformers, all in this one session. And our first speaker is the eminent Eliska Geplova from Delft University, and she's talking about quantum resources for, I think, classical and quantum variational methods. So the stage is all yours.
Thank you, Jens. Hi, everyone. Can you hear me all right? Yes. Great. Thanks. I hope you are not too sleepy after lunch. I will thank you so much to the organizers for having me. I am super happy to hear all the different talks about that the new perspectives and avenues and considerations that we should take when we are thinking about quantum machine learning. And I hope that this talk can contribute to this. Like Jens was saying, this is quantum resources. It was too long, but it's of both quantum and classical variational methods. So I am coming to this topic from a slightly different perspective. In my groups, we are primarily concerned with thinking about how to control, optimize, simulate real quantum computers in the lab. So it comes from a perspective of like a control theory or a classical simulation. Then at the same time, a long time ago, I was also a quantum information theorist. And when I think about how quantum information theory and sort of classical techniques, let's say variational methods, think about the problem of simulation, there are some interesting intersections and some interesting differences. So right now we are living in this super cool time where there is so much experimental progress, where many companies and university labs are leading with amazing papers that say, oh, now we have the quantum computational advantage we always wanted, and then maybe a week later there is a tensor network simulation that claims to do that same experiment. And this creates some kind of complicated dichotomy, right? Because how do we even say that we simulated, if we simulate approximately, that we simulate the correct thing and not just some classical thing that doesn't contain any quantumness but just happens to give the same results, or do we even care? So there is a lot of questions on this boundary. I built a big quantum computer that is doing something, and I built a simulator that is trying to predict what that quantum computer is going to do. So I feel very fortunate because all the tutorials yesterday and all talks today already set me up for this introduction part of my presentation very well, so I will go through this quickly. We all know why wave functions are complicated, right? There is this exponential scaling of literally the number, the size of the vector that I need to describe a quantum state. And that's both possible advantage of quantum computing, but also a big curse for us if we want to think about how to numerically simulate these systems exactly. And then if I think about how quantum information and condensed matter deal with this challenge, they approach it very differently. So we already heard in a morning session today all about Gottesman-Nil theorem that basically thinks about the simulatability like this. There is a group, a Clifford group, that if I am in it, I can simulate I can simulate just classically because everything scales polynomially, because I just need to keep track of this stabilizer tableaus that you heard about in one of the previous sessions. Once I start adding gates that are outside of the Clifford group, this classical simulatability breaks, and I am getting into the whole Hilbert space territory. In a condensed matter or solid state, or however you want to call it, we think about these things differently. We just say, let us think about what is some classical lower parameter ansatz we can use that is going to capture the physics well enough, but doesn't need this exponentially sized vector to describe the system, but I can still predict all the observables somewhat reliably. And so let us think about this second option in a more concrete terms. So let's forget about all the complicated set of problems and just concentrate on a very simple one, which is finding a ground state of a given Hamiltonian. So how these variational methods are deal with that is that I parameterize my quantum states. Specifically, I parameterize the amplitudes that give me the expansion of the state in some eigenbasis, and then I try to parameterize them with the lower number of parameters than expanding exactly in this basis. And then I can use specifically for the ground state search a variational principle, which is this formula, which tells me if I would write the Hamiltonian in the eigenbasis, then this psi theta would hit this equal sign exactly if I have a ground state, right? And if I have anything mixed into the state, I get something slightly bigger than the ground state energy, e.g. And because we know this, we cannot get a lower energy than the ground state energy. So if I get a ground state energy, I get a ground state. If I get a bigger than the ground state energy, I have some state that is presumably closer to the ground state. So what you can then do is to take your parameterized quantum state and just keep evaluating this expectation value and trying to make it smaller and smaller. You keep updating your parameters by some method, I will talk about some examples later, until you minimize as much as you can. And when you minimized enough, you are like, okay, I cannot make this any smaller, this is the approximation of my ground state. So pictorially, you can think about it like I have some Hilbert space. My ground state, exact correct ground state, is sitting somewhere in that Hilbert space. The blue blob is all the states that can be expressed with this variational ansatz. And I am kind of hoping that the black dot of my exact state is sitting inside of the blue blob. And if I optimize my parameters to minimize this formula, I get my ground state. Exactly how I do that, that has been, basically the history of the last century of condensed matter physics. There is super many results that are just informed by physics of the model. Think about, how superconductivity got solved, or a BEC, like someone is very smart, has some insight into the problem and makes some trial wave function that happens to have the features that capture the physics properly, then I optimize that. We heard a lot today already about tensor networks, MPS, PEPs, other types of tensor networks those are approximation based on the entanglement. I am basically just saying it's really unlikely for a lot of problems that I will care about that we will have this maxed out entanglement thing, so let me just truncate that. And some modern technique are, for example, neural networks. This is something that was pioneered by Giuseppe and Matthias back in 2017. They just say, let's take a classical neural network and use it as a variational ansatz. So in the end, on all of these methods, what I am doing is that I have some Hilbert space. I start from somewhere, and I am walking this Hilbert space until I find what is the solution that means my, for example, the variational principle for a ground state or some other optimization condition. So this is again this variational principle energy, but now there is this point that somehow I mentioned at the beginning and maybe is seemingly unrelated to this, but the thing is that Gottesman nil does not enter this equation in any point. We have a lot of states that we know we can simulate classically because they are generated by a stabilizer circuit or are generated by a stabilizer circuit with a small perturbation. But what you do classically is that you don't care about this, and you are treating all the points in a Hilbert space the same and just trying to minimize some optimization condition. And then if I do this quantumly, now I am oversimplifying super much and contradicting the talk that we heard just before lunch, but yeah, it's basically the same, except that I am parameterizing some quantum circuit instead of the classical ansatz. But if we stick with this sort of traditional interpretation of this, it's not really different. I parameterize the circuit, but again, I am calculating some expectation value on a classical computer and updating the parameters by some parameter update method. And so now there is this difference that we already also heard about in the morning, right? That if I have everything in the Clifford group, I'm good. Tableaus will do the job. If I have some non-Clifford operation, then I don't know. So the measure for this, how far I am from not being classically simulatable in the stabilizer sense. There is many, but really exciting and prominent one is called stabilizer Renyi entropy. It has this formula. You are basically calculating the expectation value of your ground states with respect to all the Pauli strings that you have in your system size. This has been introduced by Lorenzo Leone, Salvatore Oliviero, and Ali Osahama in 2022. And at that time, it kind of revolutionized this measurements of non-stabilizerness, because the previous measures were actually scaling even worse. So I'm not going to talk about this formula very much, but basically what happens when you evaluate this expectation value, you can try for yourself, for example, on the state 0 plus phase of 1, and you will find out that if you have a non-Clifford phases, you will start getting non-trivial terms in this sum, and if you don't, you just get a 0. This is still kind of horrible because it scales like 4 to the n, because you need to calculate this expectation value with respect to all the Pauli strings that you have. But at the time, this actually was a really great improved scaling of calculating this kind of non-stabilizerness. As a detour, I will not talk about these results in detail, but just to highlight this, my PhD student Arash cannot be here today, but he worked a lot on the questions of approximating this non-stabilizerness in some kind of more scalable manner. And so he's the lead author on 2 works, in which, in first one, we show that you can actually just sample few out-of-time ordered correlators to approximate the stabilizer Renyi entropy. And in the other one, we show that fluctuation of mutual information over subsystems is actually a good monotonous measure of magic. Sorry, the non-stabilizerness is sometimes called magic. You probably already heard it in the morning. So this is just something that we are looking into to approximate things better. And right now there is a lot of things happening in this field, because as we already discussed in the morning, sometimes we think about entanglement as this like a typical picture of the quantum resource. But you quickly realize that you can prepare maximally entangled state with a stabilizer circuit only, right? Just think about a circuit that prepares 2-qubit belt state. That's a stabilizer circuit. And so, okay, I can just simulate it. Classically. So what did I show if I prepare one of this stabilizer but maximally entangled state? And so people were looking into this non-stabilizerness or a magic as an extra resource. There is a lot of cool works out there. Yeah, specifically I wanna highlight what Poetry Tarabunga is doing in Trieste with respect to actually using tensor networks to calculate non-stabilizerness, and then she can do it really numerically efficiently on a really big systems. It's very impressive. So now, hopefully, I got to the point that I persuaded you that those 2 things are independently interesting. Hopefully, in this crowd, I don't need to persuade anyone that non-stabilizerness is interesting, and hopefully, I managed to motivate, well, why do we care about variational methods in the condensed matter physics? And then maybe just as like a first benchmark, when we think about merging these 2 schools of thought, we can think about, what is the non-stabilizerness of variational methods? And this is a work that postdoc in my group, Thomas and Arash, took a lead on. So, you can think about it like this. I showed you before this picture where I am walking through the big Hilbert space and calculating this expectation value of the variational principle. If I have no restrictions other than the energy has to be smallest, what can happen is this. This is cut through my landscape along one axis, and this is energy. If I have energetically 3 minima that are exactly the same, and I am just minimizing energy, nothing else, and these 3 states would be structurally very different, like it would be a different wave function. They would just happen to have the same energy. How do I know that I have a correct state, right? Because it's nice that I use my whichever is method of my choosing, physical, tensor, neural network, anything else, that I minimize this energy, but then I minimize the energy and presumably I want to calculate something with that state. And if I don't minimize it enough that I actually hit the equality in the variational principle, that I have the exactly correct state, I have some other state. And then what if that other state is wrong because it's wrong one out of these 3 minima? And so what we did in this work was to take these 3 examples, neural network quantum states, tensor networks, and variational quantum algorithms, and just try to optimize each of them to the absolute best of our numerical ability and evaluate this non-stabilizerness to see what happens across the phase diagram of an interesting Hamiltonian. So let me tell you just a little bit about how these neural network quantum states work. I am gonna skim over a lot of technical details for the interest of time, but feel free to talk to me later about it. It's just because that's one topic that haven't been covered so far today. So it just works exactly the same like any other variational state. I have some state, I wanna parameterize this in a way that it has less parameters than that it has less parameters than this exponential scaling of the exact solution. And so one way you can parameterize this wave function is just to have a neural network where weights, the blue ones, and the biases, the yellow and the gray ones, are the parameters. And after I did that, I evaluate my variational principle just the same. And then there is some specific mechanism how I calculate this expectation value and evaluate the parameters to minimize it, but we are not talking about it. This is an example of a neural network that is just a 2-layer network that has one hidden, one visible layer where everything is connected to everything, and this is called restricted Boltzmann machine. It's the simplest of these neural network quantum states. In principle, you could take your RNN, you could take whichever neural network you want, CNN, fully connected, doesn't matter, and do the same thing. It's just that maybe then the parameter update becomes harder if you have some very complicated structure. And then it's the same story. I have my ground state somewhere. The potential of this structure to parameterize some part of the Hilbert space goes like this. And then I can, for example, add more neurons in the layers, and I increase the blue blob more and more. Or I can do a different tricks, like create a new neurons that reflects on correlation structure of my Hamiltonian. This is, again, I'm not explaining this, is just a big shout out to Agnes because she developed this method. And basically it's a way to create architectures of your neural network that are informed by the terms in your Hamiltonian. And we found out that this actually works pretty nicely, and now there is some cool applications of this approach in fracton models that just appeared on arXiv last week. I was very happy about that. So there is this whole field that basically thinks about how to, engineer these neural network quantum states to be more expressive. And okay, now we are here again. So now we understand everything. I have neural network that is basically parameterizing my wave function with a polynomial number of coefficients only. I have some mechanism to stuff the weights and biases of this network into this expectation value, and I have a mechanism to minimize it. Then, when I minimize it enough, what I am going to do is to calculate the stabilizer anisotropy that Lorenzo introduced. So let's take a concrete example where we do it. We take a transverse field Ising model. We again saw it in the morning. It's this like the simplest example of a quantum Ising model. I have a nearest neighbor hopping term, and I have some transverse field. And then I am gonna diagonalize this Hamiltonian using 3 different variational methods: neural network quantum states, DMRG, and variational method. And then what Arash and Tom got when they did that is a plot like this. So here we have energy and non-stabilizerness. Energy on the left, non-stabilizerness on the right. And in the second row, we have a difference from the exact energy and difference from an exact non-stabilizerness. The blue ones is a tensor networks, purple ones is RBM, and pink ones is VQE. So on a first row of plots, you don't see anything super interesting because just all 3 methods kind of more or less hit the exact line, which is the dashed ED. There is an interesting point here that the magic or non-stabilizerness usually increases when you are hitting a criticality. This is just a side comment. It's interesting. You may know that this model has a phase transition when the transverse field is equal to 1. Then in a second row, I am seeing the difference in energy. Unsurprisingly, VQE does the worst, but like we know this, we lived through this, we will be fine with this. Smart people are working on improving this. Then we have the restricted Boltzmann machine, the neural network, and then we have DMRG. There is this part where at the low field where the DMRG is doing kind of bad, but let's just, for the sake of this talk, let's ignore this because there is some degeneracy problem with the ground state. And again, there is this degeneracy problem where all of them are kind of bad, but then DMRG starts doing super, super good in non-stabilizerness. RBM, little bit worse, VQE, the worst. So, okay, this is kind of maybe boring thing, right? Because I just said, if I have a better energy, I have a better non-stabilizerness. So, okay, this is kind of a bummer. So, it actually can get more complicated. This model has a global Z2 symmetry, meaning if I flip all the spins, I am going to have a state that has the same energy. If we think about this in just like a classical Ising model, let's not think about any transverse field, like if I have just the hopping term, the state that has everything aligned like this has the same energy that has everything aligned like this, right? And that's basically what it is. And now I can show you a new set of plots. This is the normal neural network quantum state, the restricted Boltzmann machine, energy difference, non-stabilizerness difference, infidelity with respect to the exact state. And the same for a symmetric RBM. And now it's funny because in a first line, we don't actually see much difference between the plots. Maybe you can find a small difference if you really zero down on a specific points, but in the end, these two are kind of the same. Both the normal neural quantum state and the one that I symmetrize to incorporate the symmetry, they have kind of the same energy. To be super careful here, we are including 3 colors again. Here the alpha means the ratio between hidden and visible layer of your neural network. Is this idea that what I was showing with this expanding blue blob, if I increase the number of hidden neurons, maybe I can express more. So I am increasing here to see that it's, when I maybe have a ratio of 5, it suddenly doesn't get better for a symmetric one. But it doesn't. But what does get better is a difference of non-stabilizerness. And what does get better is when we calculate infidelity with respect to the exact solution of the Hamiltonian. So what happened is this example of what I was saying before, that I may have the same energy because I hit some minimum, but the minimum is different for these two cases, clearly, because the difference in the infidelity and the difference in a non-stabilizerness was actually visible. And then the question comes whether then we can think about to use non-stabilizerness or some other quantum information measure to quickly check what type of minimum we are finding. Because the energy alone doesn't tell me much, and doing full state tomography all the time doesn't work. Yet, in quantum information, we have a lot of these metrics that tell us something about the structure of the state, and we are getting better and better estimating them efficiently with some, new tomographic or Monte Carlo methods. So this is just to say that actually just quickly evaluating the non-stabilizerness of the state tells me very quickly which of these two is a better variational ansatz, even if outwardly the energy would have been the same. There is a different side story. This is kind of developing. We also calculated fluctuations. In the world of non-stabilizerness, fluctuations of different quantities are important, and maybe that's all I will say about it. But so we calculated fluctuations in energy and fluctuation in non-stabilizerness. And in fluctuation in energy, for example, for the neural network, it kind of stays constant across the phase diagram, and that's what we want to see. We don't want to have suddenly really big fluctuations if we rerun the optimization many times, because then it's a sign that it probably didn't converge properly. At the same time, in the non-stabilizerness, in the energy, some structure starts happening, but you see one interesting thing, that the VQE is actually much more stable in the fluctuation of non-stabilizerness than it is in a fluctuation of energy. There may be very many reasons for this. We don't have a conclusive idea. Maybe some of you do. I had some simple ideas about that. Maybe because the way how the ansatz works, I'm adding the angles sort of systematically, so it has a higher chance to converge to the same state. At the same time, we are repeating this VQE block so many times that I'm not really sure this is true. We did some preliminary analysis, but we don't have a really good explanation for this yet, so that's an open question. But so, to finish, the main message of this talk is one, that quantum information and condensed matter have fundamentally different perspective on simulatability. In condensed matter, it's as long as I can minimize variational principle with poly number of parameters, no questions asked, I'm good. In quantum information, one idea is how far away I am from stabilizer group. And then the question is whether we can borrow techniques from one field to improve the accuracy of the simulation in the other. In this work that I presented today, I believe we show that a non-stabilizerness has the potential to be such a measure. And I am really excited to present here at this conference because I'm hoping that this community may have many more and better examples to sort of refine this idea. Let's take something quantum information-y that makes sense and apply it systematically in a variational methods. This field is largely unexplored, even though we even had a talk this morning about variational non-stabilizer tensor networks. So I see that you are warming up to it, so hopefully we can discuss and have some ideas. Other than that, my group is working on a bunch of other things, so come talk to me about any of these, and thank you for listening.
Wonderful. Thanks for the great talk, and also thanks for keeping in time so that we have time for some short questions. Yeah.
Did you also try the same thing by enforcing the symmetry in tensor network?
Let's repeat so it's recorded.
Yeah, thank you. You mentioned enforcing symmetry helps in restricted Boltzmann machines. Did you also try to enforce this parity symmetry for MPS?
Yeah, no, actually we didn't. And I think it would be really interesting through, in this case, because this Hamiltonian is so simple, and PS is a little bit bad example because you basically hit machine precision of your computer. So it would be hard, but I think taking some Hamiltonian that has some complex phase transition and trying there would be a very good idea.
More questions? While there's more questions coming up, I asked one also. You mentioned like energy versus stabilizerness. Now, there's wonderful, actually lower bounds for ground state energies that are not so much known, like through like convex relaxation or something. They're pretty good, so then you kind of guarantee how good the value is from below. Are there similar like bounds on what the actual value of the magic is in the variational principle, so that you know how far off you must be or must not be?
Yeah, so you are asking, of course, exactly correct question. That's the main problem with this, right? Because if I would have, I would be just, let's minimize the magic instead and be done with it. So there are two things that are more vague that we notice. Usually that the magic saturates around the criticality, so that's one thing. And then in the time evolution, it sort of increases smoothly. So those are two things that one could use, but nothing as strong as a variational principle.
I see.
Great question.
There was another question coming up here.
It's kind of a follow-up to Jens's question, which is, in this case, because you're seeing as a function of age the Ising model, for very large age, your state is fully aligned, so it's a stabilizer state. But in general, do you expect that this will be useful in cases where, you have a model, but none of the states are going to be a stabilizer state? Because this is a very particular example, right, where one of your phases is actually a stabilizer state.
Yes, so that's a great question. So how we came to this was actually trying with a much harder Hamiltonian, and what happens there is that when I initialize this random ansatz in a Hilbert space, I just systematically get magic that is much higher than the actual ground state. It's like random point in a Hilbert space is going to have a maximum magic, but usually ground states of the interesting Hamiltonians are structured in some way. Yeah, this is kind of a vague reply, but I think I'm saying that it's not that this state has the non-stabilizerness works because it has a structure. It's even funny because the structure here is so simple that the unsymmetrized neural network just learned it anyways, right? It's much more interesting in a cases where you don't do that, and there is going to be many more minima, and therefore I would expect that there will still be differences in the non-stabilizerness. But again, there is no statement like the correct state has the lowest. It's just that the correct state has a different.
Okay, I think we should move on and thank again Eliska for this wonderful talk. So next